Welcome everyone to our final lecture. So today we're going to continue talking about concurrency issues when we have multiple transactions. And at the end of the last lecture, if you remember, we talked about how we can implement the locking operation without resorting to additional hardware functions. And now we're going to return to the deadlock problem and how it can be prevented, or if we allow it to happen, how it can be detected. Okay, so just to remind us what the deadlock is, let's look at this example here where we have two transactions, T1 and T2. And in transaction T1, we're first acquiring a read lock on item I, then we're reading item I. Then in transaction T2, we're acquiring a read lock on item X, and then we're reading item Y. So that's all fine, right? Because, so actually, sorry, this should be X here, not Y. Because I can't read an item without acquiring a lock on it. And over here, we are trying to acquire a write lock on X. And now T1 has to wait because it can't acquire write lock. Because T2 already holds a read lock, okay? And the read lock and the write lock is an exclusive lock, so you can only acquire it when no other transaction holds a lock on that same item. Now then we proceed executing operations of transaction T2. So T2 tries to acquire a write lock on Y, and this also doesn't work, right? Because T1 has already acquired the read lock earlier on for Y. So T2 will also need to wait for item Y to become available. Okay, and since both of these transactions are waiting now on each other, we have a deadlock between these two transactions. So a deadlock means no other operations are going to happen unless we abort one of the transactions. And one interesting point to note here is that these two transactions are following the two-phase locking policy, the basic one, right? Because they're actually not unlocking anything, they're only locking. So that's fine. We have one growing phase, and if we let those two transactions continue, maybe we have one shrinking phase, but still we are running into a deadlock. Okay, so let's see what we can do to prevent deadlocks from happening. So one strategy we actually already seen before. So if a transaction simply locks all the at the same time, like in one atomic step, the locks for all the data items that it wants to access before it begins its execution, then this will prevent a deadlock, okay? And the reason for that is that the transaction never waits for a data item while holding some locks. And this is in fact exactly what is done in the conservative two-phase locking policy that we discussed in the last lecture, right? So in there we had to lock all the locks in advance, and note that we're not locking them one after the other. These locks, we're acquiring all the locks at the same time. That's the important point. If you require the locks one after the other, then you can still again run into a deadlock. Okay. So basically there's no hold and wait condition here. So this conservative two-phase locking is in fact a protocol that prevents deadlocks from happening, but it limits the amount of concurrency that we can get, because if you compare it to, for example, strict two-phase locking, then you can see that it's much harder to make progress if there are many transactions, because each transaction needs to wait until all the locks that it wants to access throughout its execution are available, which is a much more stringent condition compared to the ones that we're facing with strict two-phase locking. Okay, so let's look at deadlock detection and resolution. So now we are allowing deadlocks to happen. And this is exactly what the case when you look at protocols such as strict two-phase locking, right? So we saw last week that it's possible that you run into deadlocks. And in fact, in the tutorial, we saw a few examples for that. And of course, we don't want to be stuck with that deadlock. We still want to have a functioning system. And therefore, the scheduler will maintain a so-called wait for graph to detect cycles in the sense of transaction 1 waits for transaction 2 waits for transaction 3, and transaction 3 waits for transaction 1. Okay, so we have like a cyclic wait here. I'll talk about this wait for graph in a second. So if you do have such a cycle, then one of the transactions that are part of this cycle will be kind of aborted and rolled back. Okay, so that transaction needs to restart its execution. So it becomes, it's selected as the victim. So I already mentioned the wait for graph. So let me formally define it. So again, it depends on which items we're locking and when. And similarly, for as the serialization graph, we have nodes in the graph where one node corresponds to a transaction. And if a transaction Ti is blocked by a transaction Tj, then we're adding a directed edge from Ti to Tj. And you can read this edge as saying that Ti waits for Tj. Okay, that's the meaning of an edge in the wait for graph. That's where it got its name from. Now, if Tj releases the lock, then we're removing that edge. Okay, because now Ti no longer waits for Tj. So what this means is that this wait for graph may change over time. So it's a dynamic graph in the sense that its edges may change as you progress your transactions. Okay, so initially, in fact, if you look at your wait for graph, it will just consist of the nodes without any edges, right? Because no one has no one is holding any locks yet. So no transaction is waiting on any other transaction. Okay, and as you start executing the operations, you will add more edges, you might remove some, and at some point, you might detect a cycle. Okay, so when there is a directed cycle in the graph, for example, from Ti to the Tj, Tk, and then back to Ti, then you will need to select one of the transactions to be aborted. Now, how do we select the transaction that we should abort? Because in principle, we could select any one of the ones that form a cycle. So this process is called victim selection. And usually we'll try to select the transaction that has the shortest running time so far. Okay, so that was the transaction that is kind of the youngest transaction, will be the one that you're trying to restart. Why do we want to do that? Well, the intuition behind this is that the older transactions have already done a lot of work because this was started earlier, so we don't want to waste that work. We want to keep those around, and instead we're going to try to just restart the ones that have only started recently their execution, because that might be less costly. Of course, this is just a heuristic. It might not give you like optimal results in terms of the time that you can save here, but it has worked well in practice. Okay, so one problem with this approach here of cycle detection in the wait for graph is the matter of determining when the system should check for a deadlock, right? Because as I said, this is a dynamic graph, so these edges are coming and going over time. So one possibility is to check for a cycle every time an edge is added to the wait for graph. Okay, so that's the easiest. So basically each time you're executing a locking operation, you can check immediately if that is causing any if that is closing any cycles in your wait for graph, and then you can react to that. But in practice, this is usually not done at every locking operation because this would add an excessive overhead. And most locking operations are fine, they don't cause any cycles. So you don't really want to check with each locking operation. So there are alternative heuristics that we won't be talking about, such as using, let's say, a time-triggered approach where every few, every few milliseconds I can check for a cycle, or when a specific number of locks has been acquired, then I can check for a cycle, and so on. Okay, so let's look at an example here. So we have 3 transactions, U, V, and W. And these are the operations here. So they're accessing 4 different objects, A, B, C, and D. So let's draw the wait for graph. And of course, we need one node for each transaction that we have. So we have these 3 nodes here. Okay, so initially we're acquiring a lock for D. When we execute this, then we're acquiring in transaction V, we're acquiring a lock for item B. That's also fine. Doesn't cause any edges to be added here because nobody's holding this lock yet. And then I'll jump back to transaction U. I'm acquiring a lock for item A. And then I'm acquiring a lock for item C in transaction W. And now I'm trying to acquire a lock for item B in transaction U. But now I have a problem, right? Because up here, transaction V has already acquired a lock and it hasn't released it yet. So I need to add this edge from U to V, right? So U is now waiting for V to release that lock. Okay, let's continue. So next, we will try to acquire a lock on C, but W has already acquired a lock on C. So now we have an edge from V to W. And finally here, W is trying to acquire a lock on A. And of course that doesn't work because we already have acquired a lock on A here in transaction U. And therefore we now need to also add an edge from W to U. Any questions so far? Everyone's so silent today. Okay, good. Good. Well, I was worried that I was muted this whole time and maybe nobody could hear me and I didn't know. That would have been a problem, I guess. Okay, so let's continue. So let's look at something slightly different, namely deadlock prevention using so-called timestamp. So here the goal is to prevent a potential deadlock from becoming a deadlock. Okay, so so each transaction is now assigned a unique timestamp, which we are abbreviating as TS. And what can we use for timestamp? Well, usually just the creation time. Now, in some cases, you might use a priority instead of a timestamp, but for simplicity, we're just going to use timestamps here. So a timestamp might not always be that clear what it is, because it can depend when we have a distributed database that is distributed among multiple machines, then these machines might have different clocks, right? And in that case, you might also use something like the so-called site ID, where site refers to the machine where you're running, in addition to the creation time. All right, so now there are 2 rules for deadlock prevention using these timestamps. The first one is the so-called wait die rule. And this is a non-preemptive rule because it doesn't interrupt an already running transaction. And I will just first very succinctly state this rule, kind of like a program. So it can be stated just by a simple if condition. And then we're going to talk about what this if condition means. So if the timestamp of Ti is less than the timestamp of Tj, then Ti waits. Okay. Otherwise, Ti dies. Okay. And maybe I should also mention what Ti and Tj are. So Ti is the one that is requesting a lock that is already held by Tj. Okay. So you can think of having this edge here in your wait for graph. All right. So now what this wait die rule does is it will compare the 2 timestamps. Okay. So, and what this says is that Ti is only permitted to wait if Ti is older than Tj, right? So if its timestamp is less than the timestamp of Tj. Okay. On the other hand, if Ti is younger than tj, meaning its timestamp is greater than the timestamp of tj, so this is the else branch here, then ti is simply restarted. Okay, and that's where the name of this rule comes from, right? So in either you wait or you're being restarted, you die. Okay. Now, when ti is restarted, it will restart with the same timestamp that it had just before. Okay, so it doesn't get like a new timestamp, because we want to avoid that a transaction is always like the youngest transaction, because it's being restarted all over again. Oh, I saw there was a question in the chat just now, and it has already been answered. Yeah, right. So this is a non-preemptive rule because it doesn't interrupt a transaction. Okay. So we'll see an example of a preemptive rule in a second. So this is the wait die rule so far. All right. And of course, the intuition behind this is that now, if you do restart TI and TI requests again the access to the same lock for the second time, well, maybe we're lucky and TJ has already completed its execution, and then TI's request will succeed. All right. And note that the purpose of this rule is to prevent potential deadlocks. Okay. So it doesn't mean that if you don't follow this rule, you will actually get a deadlock. But we know that if we do follow this rule, we will never run into a deadlock. Now, the second rule that is used here, there's a question in the chat whether this rule has any limitation, like limitation as in. So basically, you're going to execute this rule every time that a transaction TI wants to acquire a lock that is held by some transaction TJ. So whenever you have this scenario here, you're just going to apply this rule. Oh, no. So this will always stop a deadlock from happening if you apply this rule. Okay. So it's not possible for you to run into a problem with this when you apply this rule consequently. We'll see in a second why that is the case. So let's look at the second rule. This is the wound wait rule. And this is now a preemptive rule because it may interrupt an already running transaction. Okay, so again, I'm stating it succinctly here as a if-else branch. And again, we have TI, the scenario where TI wants to request a lock on an item that is already held by TJ. So let's keep that in mind. So now if TI is an older transaction than TJ, and TI is requesting a lock that is held by TJ, right? Then we're just going to restart TJ, right? So TJ is already running. It's the younger transaction. And we're just going to interrupt it. So we're preempting it. And that's where the name, that's why this is a preemptive rule. Okay, so, and the reason why this is called wound wait rule is that we can think of like this older transaction TI as wounding the newer transaction TJ by restarting it. Okay, and otherwise, if TI is a newer transaction, then it needs to wait. Okay, so that's why this is the wound wait rule. So again, here's the textual interpretation of that. So if TI requests a lock that is already locked by TJ, TI is permitted to wait if and only if TI is younger than TJ, right? So if TJ is, if TI is older than TJ, then TJ is restarted. And again, in the same way as in the wait die rule, so it's restarted with exactly the same timestamp that it currently has. Okay, and oh, and of course, one important thing that I forgot to mention is, so when the transaction here is restarted, then it loses, of course, its lock. Okay, so and in that case, the lock goes to TI, right? So since a transaction that is restarted has all its locks released, then TI can continue its execution. So there's a question whether smaller means older. So yeah, so smaller timestamp means transaction is older, right? So right, so you can just think of starting like a time 0, and then you can, you know, give a timestamp to each transaction depending on when they start the execution. You just count up. You can even think of them as like integer values, right? So the first transaction that starts has value 0, the second one, you know, and then there's some operations, and then whenever the next transaction performs the first operation, it gets just the timestamp of the number of operations that have happened so far. Okay. So there's a good question. What if both transactions have the same timestamp? So, well, we can kind of exclude that, right? So if I just simply count, so since we're assuming that the operations aren't happen like really exactly at the same time, so there's some ordering of these operations in the model that we're assuming here. It's also not possible that two transactions have exactly the same timestamp. If you like, you can think of it, you know, as giving each transaction an ID, and then breaking the ties using those IDs if you want to use, for example, the real time as the timestamp. And if I assign two transactions the exact same real time on a, let's say, multiprocessor system, then I can use the transaction ID to break ties. All right. Okay, so we've learned now about these two methods, wait die and wound wait. And the point is that both of these methods may restart the younger transaction. Okay, so the older transaction is never the one that restarts. And why do these two methods prevent the deadlock? Well, I'm not going to give you a formal proof, just I'm trying to give you some intuition. So both of these methods prevent a cyclic wait. So for example, if you have like a deadlock cycle in your wait for graph, so you have an edge from T1 to T2, from T1 to T3, and so on, all the way to transaction Tn, and then back to T1, then this is actually impossible, right? Because you know, if we have this sequence that T1 waits like transitively on Tn, then Tn is not allowed to wait for T1. Okay. Because if you look at these two rules, you can see that a transaction can only wait for younger transactions. All right, if you have the wait die rule. Now, if you look at the wound wait rule, then a transaction only waits for older transactions. All right, so you can't have a cycle because at some point the cycle is broken. And yeah, as I said, this is not a formal proof. It's not too easy, not too difficult to actually prove this formally, but this is beyond the scope of this class. And now let's look at some examples for using these rules. So here we have two transactions, U and T, and we're assuming that the timestamp of U is less than the timestamp of T. Again, as I said, you can think of like, you know, the timestamp in terms of like counting the operations, but that's just one way. And also what I mentioned is that sometimes we're not really looking at timestamps, but we're giving them priorities. Okay. All right, so this is the schedule that we have here. Okay, so let's see what happens when we use the wait die rule. And before I show you what happens, let's just assume that we don't use either of the two rules. So what will happen? Well, here I will need to acquire a lock on A before I can do this read. So we'll need to acquire a read lock. Then I will need to acquire a write lock on B. Then here we'll need to acquire a read lock on C. And here we'll also need to acquire a write lock now on A. But that's a problem because I already have a read lock here on A. So this write here will be blocked. And here this write in transaction U is also going to be blocked because I need to acquire a write lock. And I've already acquired a read lock over here in transaction T. Okay, so that's a problem. So we're running into a deadlock here. So let's see how the wait die rule can help us. So what is going to happen here? Well, is the rule going to trigger anything as I execute these two operations here? So I'm acquiring a read lock, then a read A, then I'm acquiring a write lock, then a write B. So is anything going to happen for that? Assuming that I follow the wait die rule. No, right? Because no one else is holding any locks on A and B. So the rule won't be triggered, right? So the rule only comes into play when some other transaction actually already holds a lock. Okay, so this is fine so far. And similarly for this read C here, so I will acquire a read lock, and I also don't trigger the rule because nobody is holding a lock on read yet. Oh, sorry, on C yet. And then I can read C. And now this is where the part where things are getting interesting. So now I'm trying to acquire a write lock on A. Okay, so what the wait die rule is going to do is it's going to restart T. Why is it going to restart T? Well, because T wants to acquire a lock held by U. So we have this setting here in our wait for graph, right? But we assumed that the timestamp of T is greater than the timestamp of U. Okay, so we are in the else branch of the wait die rule, and therefore the younger transaction, meaning T, is going to be restarted. So what happens when T is restarted? Well, it loses all its locks. So in particular, this read lock here for C is released. And therefore, transaction U here can continue. So it can acquire its write lock for C and then write C and so on. Okay. And here it can just release all the locks because it's done with its operation. All right. And finally here, transaction T can acquire a read lock on C and then perform its read on C, right? So this is the point where transaction T has restarted. Okay, so it's trying to again, do its operation, and then it will do a write on A and so on. Exactly. So when I say restart, everything that the transaction has done is being rolled back. So it's an aborted transaction, and then we're just restarting it from scratch, but with the same timestamp that it had before. Okay, so let's look at this exact same setting, but now let's look at what happens when we use the wound wait rule. All right. So now things are a bit different here, right? Because over here, so again, in these first three steps, nothing is going to happen. So we can read A, write B, and here I'm omitting all the locking operations. So you need to think of like, acquiring a read lock before doing the read and acquiring a write lock and so on. So just imagine these operations, these locking operations to be there. So for the first three operations, nothing happens. And now when we come to this write of A here, when we try to acquire the write lock, transaction T will be blocked, right? Because we already have a read lock over here. And what is going to happen? Well, we're using wound wait, right? So since T is, and again, have this setting here, right? So T is trying to acquire a lock that is held by you. And T is the younger transaction. Okay, so it is allowed to wait in the wound wait rule. All right. So we're not being restarted here in transaction T. And then later on, as transaction U is trying to execute this write of C here, so it needs to acquire a write lock for C. So now again, we are going to apply the wound wait rule, right? Because now we're trying to add an edge from U to T in our wait for graph. And what is going to happen here is now that transaction T, which is currently running, is going to be restarted. So it's going to be preempted because T is younger than U, right? So this older transaction U here wants to get this write lock for object C, and transaction T already has a read lock, so transaction T will be restarted. Okay, and of course afterwards, this read lock, or rather not afterwards, but once T is restarted, this read lock here is going to be released, and you can acquire the write lock on C. Yes, so restarting means that you unlock all the locks that you have acquired, right? So think of restarting as undoing all the steps that you did. In particular, that includes acquiring all the locks, right? So a transaction that is being restarted doesn't hold any locks at all. There's another question in the chat. So what do you mean? Does it so unlock occur in the same transaction or the both transactions? Yes, I'm only unlocking the locks for that single transaction that is being restarted, right? So the other transactions, of course, keep the locks that they have so far. Good. Let's move on. All right, and since we are not having any more tutorials, since this is actually our last lecture, let's do one more example of such a schedule. So here we have a schedule for two transactions, T1 and T2, and we're assuming that T1 has an older timestamp than T2, right? So this holds. So we want to first see what we get if we just used strict two-phase locking for this schedule here, and then we want to look at what we get with the wait die method, and then for wound wait. Okay, so let's look at the schedule. So strict two-phase locking will give us something like this. So we need to acquire a read lock, which I'm abbreviating as RL, on A, then I'm reading A, and here I'm acquiring a read lock on B, then I'm reading B, and then I'm acquiring a write lock on B. And now I have a problem because I'm blocked, right? So why am I blocked? Well, because transaction T2 has already acquired a read lock on B. Okay, so and maybe one thing that we can, so basically if you look at the wait for graph, you have this picture here. In a second, once we have this, right? So our wait for graph currently looks like this. and transaction T1 is blocked here, so it can't execute the write. And so now in transaction T2, we also try to execute the write on A, so we need to acquire a write lock on A. And now we have this edge here in our wait for graph, okay, because already transaction T1 has acquired a read lock. All right, so you can see that we have a deadlock, right? So both of these transactions are waiting on each other now. And this is the point where we're going to use the wait die method as a first step. Okay, so let's see what happens here for the wait die method. See if I can erase something here. Oh, actually, let's not erase anything. All right, so what is the result going to be here? Okay, so when am I going to use this method? So what happens here in this write lock? So I'm trying to acquire a write lock on B. And we're assuming that the timestamp of T1 is less than timestamp of T2. And using the wait die method, what is going to happen? Any transaction being restarted? No, right? In fact, transaction T1 will just wait. Okay. And so we just continue, right? So now transaction T2 gets to, or rather tries to execute this right here. So it will acquire the write lock on A. Now transaction T2 is younger than transaction T1. Okay, so, and the transaction T1 already holds the lock on A. So transaction T2 is being restarted. All right, so as we just said, restarted or dying means that it's going to release all its locks, in particular, this lock here held on B. And therefore, now transaction T1 can successfully acquire the write lock and then execute the write on B. All right. And then we're done with transaction T1. So the final order of the operations here will be that we are executing transaction T1 first, and then now the restarted transaction T2 can also continue, and it will execute both of its operations. Oh, T2 is not blocked. So the point is we restarted T2. Okay. So when we try to acquire this write lock here for A, we checked in the what to do in the wait die rule. And since T2 is younger than T1, it's being restarted. So it's not blocked. It's just going to restart. And therefore, all its locks are being released. So it's not waiting for anything, right? Yeah, exactly. So T1 will execute first and then T2. All right. Okay, so this is the first part. Okay, so now let's see what happens when we use the wound wait method. Right, so again, these operations appear all fine, right? Because nobody holds a lock yet on these items A and B. Now it again becomes interesting once we reach this write lock on B here. Okay, so what happens here? Well, T1 is the the older transaction. Okay, so what is going to happen at this point? when T1 tries to acquire this write lock? Will it succeed or will it be blocked? Yeah, exactly. So it will succeed in acquiring the write lock because it's simply going to restart T2, right? So it wounds the already running transaction T2. So transaction T2 is being restarted. For some reason, the color has changed to black. Oh, well. Okay, and therefore, now all the locks here are released from T2. So therefore, this write lock will be successful, and T1 can write B. And then finally, the restarted transaction T2 can perform its operations. Okay, does that make sense? And note that this wait for graph here, it changes over time. So in particular, once a transaction restarts and all its locks are released, then some of these edges here go away, right? So in fact, if this transaction T2 is restarted, what is going to happen with the graph? Which edges are still going to be there? So actually, well, the transaction hasn't yet. So if I restart the transaction, then it hasn't. Then all of these operations here being rolled back, right? So the transaction hasn't done anything. So it can't be waiting for any other transaction. Okay. So in fact, we won't have any edges. In our wait for graph, if I restart one of these two transactions, because nobody's waiting for any other transaction until we, execute the next operation. And in this case, the next operation would be this write of B here, and obtaining this write lock of B first, of course. So this also does not have any edges, right? Because so T1 will execute first, also in this case, in the wound wait rule. So in both cases, the schedule will be T1 and then T2. Okay, so there are quite a few questions now. Let me see. So the first one that I haven't answered yet, I think, is that these rules can be used with C2PL and S2PL. So actually, well, we do use them with strict two-phase locking, but we wouldn't use them with conservative two-phase locking, as someone has already pointed out in the chat correctly. The point is that for conservative two-phase locking, we already are guaranteed not to run into any deadlocks, right? So we don't need these deadlock prevention protocols. So you can think of this as an alternative to conservative two-phase locking. But you would use these protocols together with strict two-phase locking, because strict two-phase locking can run into a deadlock. Okay, and the second question here is write lock of B doesn't need to wait. You mean this here? Okay, so if we're executing the wound wait rule, right? So so what's the picture at that point? Well, at that point we're in transaction T1, and we're waiting for transaction T2 in a sense, right? We're trying to get this lock on B, and transaction T2 is holding this lock on B. So T1 is waiting for transaction T2. And now we just need to look at what the wound wait rule does, right? So so the timestamp of T1 is less than the timestamp of T2. So T1 is the older transaction. And therefore, we're going to restart the younger transaction, T2. All right. So okay, so that's why for this, there's no way we can be blocked here. So T1 is not blocked at all because T2 is immediately restarted, and therefore all the locks that are held by T2 are being released, in particular this lock here in B. And so T1 can successfully immediately get that lock. Okay, so let me see. There was, not sure if this is a question. The wait die for younger means younger determines the restart time. Well, the difference is that in wait die, so in both cases, in both of these rules, it's only the younger transaction that is being restarted. So the older transaction is never being restarted. Not sure if that answers your question. So
sorry, I mean that. Well, sorry, I mean that for the like the won't wait. You know that the WB determines the restart. At that time right B in T1 will determine the restart of T2, but in the but in the wait T2, but in the wait die, the WA determines the restart of T2. WLA in T2 determines the restart of T2.
yeah. Oh, so that's what I mean. Okay. Yeah, so that's the difference. So that's why one of these rules, I mean, that's why we said, that's why we said the wound wait rule is a preemptive rule, right? So it can, so one transaction, the older transaction can wound the newer transaction, the younger transaction, right? Whereas the wait die rule is non-preemptive, right? So a transaction, so only a transaction, if the younger transaction tries to acquire a lock and that lock is taken by an older transaction, right, then the younger transaction will restart itself in a sense.
I see, but in my opinion, but wait die should call it a suicide for T2, and won't wait means the queuing.
Sure, but it's usually not the transaction that decides that, right? It's basically the scheduler that makes this decision. So it's yeah. So all these restart, so all these protocols are being executed by the scheduler. So the transactions are just faithfully executing SQL statements, basically. So they don't really have any say in this. Yeah. So, we saw a difference here in terms of what happens in this transaction, right? So in both cases, we will end up, restarting T2 because it's the younger transaction. But the difference was that for wait die, we restarted T2 because of at the point when T2 tried to execute this write lock, try to get a write lock for A. Okay, whereas for wound wait, we already restarted T2 as soon as T1 tried to acquire this write lock on B. So that is the difference. Okay. Well, in wound wait, you might also wait, right? Okay, so All right, so maybe let's just, so this was wound weight, right? This was the wound weight. Oops. And now let's write this thing again. For weight die. Just so we have both examples next to each other. So here we need to wait, right? That's the weight die rule. So the older transaction, which is T1 in this case, will just simply wait for the younger transaction. And then the younger transaction tries to acquire the write lock on A and will immediately restart itself. Okay. And then down here, we can finally acquire this lock on B in T1 and then perform the write on B. All right. So, I mean, wound weight doesn't wait in this scenario, right? So there is a possibility that wound weight needs to wait, right? Because if you have like, you know, if a younger transaction tries to acquire a lock that is held by an older transaction, then the younger transaction will wait. Okay. All right, so I see that I'm already cutting into the break. Okay, so let's continue at maybe 5:03. All right, so let's continue. So yeah, so this was this example here for using weight die and wound weight. And you can find more information about these things in the textbook. There's one more example that I might want to do about these wound weight and locking protocols in particular. But before we get to this example, let's see if we have enough time. I want to say some things about the final exam, since today's our very last lecture. So some general remarks. So you probably already know that it's going to be an online exam. So it will be held using Canvas quizzes, and we're going to use Zoom. Okay, oh, I missed some questions in the chat. Is that right? Let me see. Yeah, but I guess they've already been answered. Right, so they're going to be around 5 larger questions on different topics. And keep in mind that you need to achieve at least 30% on the final exam to pass the course. Unfortunately, there might be some students in every year that don't pass this. So even if you have high grades on the coursework, there's nothing much that we can do if you get like 0 points on the final exam. Yeah, I mean, these things are set for, you know, as far as I know, department-wide. So all the courses that I taught here have this 30% built in somehow. But yeah, it is what it is. So another thing that I want to mention is that, well, I only taught this course once before, so my experience with the exam is limited. But what I saw was that a lot of students struggle with the SQL queries and relational algebra queries kind of questions. So I would encourage you to practice these beforehand. And now I will just go through some of the topics that we discussed and remind you of some of the things that I think are important. So let's start not at the very beginning, but close to the beginning. So we talked about the R model and how we can map it to the relational model. So we had this 7-step algorithm for that. And in particularly important there were the mappings of these binary relationship, these are binary relationships in the R diagrams to the relational model. Okay, so we learned about 3 different approaches for doing so: foreign key approach, the merged relationship approach, and the cross-reference approach. Okay, so it's important to know when you can use which of these approaches. For instance, you can only use a merged relationship approach when you have a one-to-one relationship in your ER diagram. All right, and also things like total participation constraints play a role when you can use which of these approaches. All right, so keep all of that in mind. And depending on which approach you're using, this also kind of determines the number of relations that you get when you're trying to map, you know, a binary relationship from the ER model to the relational model. So many-to-many, well, for many-to-many, we're usually using this relation approach, right? So we're basically adding one more relation. Okay, so when you have an M-to-N relationship in your ER diagram, you might end up with 3 relations in your relational model rather than 2. We also talked a lot about functional dependencies and how you can identify the candidate keys for a relation. All right, so we saw some kind of algorithm for doing that. And that algorithm was about, you know, like whenever you have some set of attributes, you need to find out if the closure of these attributes contains all the other attributes. In that case, it is a super key. And if that set of attributes that it started with is minimal, then it's also a candidate key. Now, related to these functional dependencies, we looked at the Boyce-Codd normal form, also abbreviated as BCNF, right? And it's kind of a simple definition because you can think of it as like whenever you have this non-trivial functional dependency, X determines A in your relation, then X must be a superkey. Okay, so you can't have like these transitive these transitive functional dependencies. If you have a transitive functional dependency, then your relation is not in BCNF. And now I'm jumping towards file organization, which was the subsequent topic. And there what we talked about was, well, we talked about a lot of topics, but I would just want to remind you of how to handle these overflows when you have the hash functions. Okay, so we had these buckets here, right? And each bucket corresponds to kind of like a disk block. And if you hash too many items into the same bucket, then your bucket will overflow. So there are multiple strategies how you can deal with that. And one of the strategies here is that you just have these overflow buckets. Okay, so for instance here, all of these items were hashed to the same bucket number 2, and also this item 182 will be hashed to bucket number 2, but it was full. So we need to let our record pointer here for this bucket point to some overflow bucket, and not just to some overflow bucket, but to actually a record in the overflow bucket. That's why it's a record pointer. Okay, so if this overflow bucket itself is full, right? So we might need to add more items to other overflow buckets. So in this case, 652 was also hashed to bucket number 2, right? But so we have to follow this chain to actually get to that item. Yeah, so the slides are already online. So I updated them just before the lecture. So this also includes these slides here. But I can't recommend preparing for the exam just by studying these last slides. That's a very dangerous strategy. So yeah, so I think we might, so this course is actually, or rather this part of the course that I'm teaching is actually one of 3 sections. And since you might need to enter, you might need to enter things that are like relational algebra queries by typing text into the text box. We might give you some extra practice exercises for you to do that. But yeah, probably next week. And yeah, so this was about the chaining. And we also talked about extendable hashing, right? So this was a way to kind of gradually grow your hash table. So each bucket has this local depth, and you have these global depths for your directory. And only when the local depth of some bucket starts exceeding the global depth, that is when you need to double the size of your directory. No, actually, the grading will be combined. And in fact, we have one common final exam for all three sections. So yeah. I'm not sure what it means by the web answers are always wrong. But yeah, I mean, for the practice exercises that we're going to upload, I will try to also include the answers. Or rather, one possible answer. Okay, so this was extendable hashing. Everything else had been different. What has been different? What has been different from what? anyway, let me continue here for now. So we also talked about records and how they're stored, right? So you can think of your data file as like a sequence of records, and maybe some metadata. And each record is, you can think of it as like a tuple in your table. So each record will contain some field, and the fields may be of fixed lengths or variable lengths. So we had various ways of storing these records, right? So you can store them spanned or unspanned. And depending on which one you use, that gives you a different, you know, especially if it's unspanned, you can calculate the blocking factor. So that's an important metric that you should remember. And we spent quite some time looking at these indexes, right? So we looked at various examples. I believe you also have some in your homework. So it will be good for you to remember how to work through these examples here. Yeah, this was another one, right? So we're looking at the number of, so basically here we, what we're doing is we need to look at the number of records that we have, and also at the number of index entries that we need and so on. That depends on whether you have a dense or a sparse index. So keep that in mind. And here in this example, we're looking at the total number of block accesses, right? So yeah. Now, we also looked at multi-level indexes, right? So this was basically like thinking of your first level index as now like the data records in a similar way, and just building another index on top of that. That's one way to think of these multi-level indexes. And then you just repeat that procedures, this procedure until you end up with an index that fits into a single block, right? Because each time you add a level on this, the number of index entries that you need will be shrunken down by the blocking factor that you get, by the index blocking factor to be precise, also called fan out. And so at some point you will reach a level where you only have a single block, and that will be your last level. Okay, and also for these multi-level indexes, we looked at the number of block accesses that you get. So more recently, we talked about transactions, and in particular, when schedules of transactions are serializable. So we looked at conflict equivalent schedules, right? So we had these conflicting operations. So read writes are conflicting to different transactions, and similarly, write writes are also conflicting. Okay, and whenever you have such a conflict between two transactions, you can add, or you can think of them as, you know, kind of accessing the same item in a somewhat dangerous way. And we defined this notion of conflict serializable schedule as, so we're saying that the schedule is conflict serializable if it's conflict equivalent to some serial schedule, meaning all these conflicting operations are happening in the same order in the two schedules. And based on this, we defined the serialization graph. And keep in mind that the edges of the serialization graph depend on these conflicting operations. And in contrast to the wait for graph that I mentioned just before, this is not a dynamic graph, right? So we're not like removing edges here. We just keep adding them as we go along through the transactions. And yeah, of course, one important point about the serialization graph is that we can check for cycles to see whether a schedule is conflict serializable. Okay, so now the schedules can be classified in terms of their recoverability. So we had this notion of a recoverable schedule when we have two transactions, Ti and Tj. So if Ti reads an item written by Tj, then we say that, then Tj needs to commit before Ti to make this a recoverable schedule. And then we looked at some recoverability conditions of different strengths, where just being recoverable is kind of the weakest version. The next stronger one is cascadeless. And this has the additional restriction that every transaction reads only items that were written by already committed transactions. And the nice thing about these cascadeless schedules is that it avoids these cascading rollbacks where one transaction aborts and then this causes another transaction to abort and then another transaction to abort and so on. And the strongest condition was for a schedule to be strict, right? So there you need to delay the reading or writing of an item until the last transaction that updated that item has already committed or was aborted. All right, and last week we talked about deadlock prevention protocols. I would also recommend you to look at these again. So one way to do this is just to use conservative two-phase locking. Actually, this is not from last week, this is from this week. I'm already forgetting when I was talking about things. So, of course, conservative two-phase locking achieves deadlock prevention, right? Because we don't have any hold and wait condition. And of course, just before I talked about the wait for graph, so it's also important to remember how this wait for graph is constructed and you know what it is used for. And now I think, yeah, we still have some time to go back to this example that I wanted to do. Okay, so let's look at this slightly more involved schedule of 3 transactions. So let's first assume that we're using C2PL, conservative two-phase locking. Can we get any deadlock here? No, right? Because as we just learned, conservative two-phase locking avoids deadlocks. Okay, so let's not worry about conservative two-phase locking. It makes things kind of boring here. So let's assume that we're using strict two-phase locking. So are we running into any deadlocks here? Yes, we are, right? Because, and so which transactions are involved in a deadlock? Because sometimes only a subset of the transactions are involved in a deadlock. So what is T1 waiting for? T1 is waiting. So when it executes this right here, it will need to acquire a write lock on X, right? And it can't because it's so it waits for the lock of X, right? And you know, exactly. So that's the problem, right? So T1 is waiting for T2, and T2 is waiting for T3 because of these two operations here. What about T3? Well, it does this right here of Y, so it's waiting for this lock. Okay, so unfortunately, we have like a cycle that involves all 3 of them. Okay, so T1, T2, and T3 are all involved in a deadlock. If we just use strict two-phase locking. All right, and now let's just let's just assume that we're using basic two-phase locking, right? So what was basic two-phase locking? Well, it just assumes that we have like a single growing phase and then a single shrinking phase in terms of lock acquisition, right? So this was this picture here. So I keep acquiring locks until at some point I start releasing locks, and then I no longer acquire any locks. All right, so and let's make some assumptions here. Let's assume that the timestamp of T1 is less than the timestamp of T2 is less than the timestamp of T3. Okay. And let's assume that we're using wound weight. To avoid having a deadlock, because if we don't use wound weight, if we're just using basic two-phase locking, we're also going to run into a deadlock. All right, so let's see what happens here. And maybe I'll just write this down here again. Okay, so, well, we're using basic two-phase locking, so we're going to acquire here read lock on X, and then we can read X. And then here we're acquiring a read lock on Z. And we're reading Z. Okay, and then the next step, we want to acquire a write lock on Z here. All right, so you can see that this is already a step where we need to be careful, right? Because transaction T3 has already acquired a lock on Z. So at this point here, what is going to happen? We want to use the wound weight rule. So this transaction T2 here, which is an older transaction, right? Because we assume that the timestamp of T2 is less than the timestamp of T3, wants to acquire this lock that is held by transaction T3. So what are we going to do? What is the wound weight rule going to do? Exactly, right? So it's going to just restart T3. Or wound T3. All right, and therefore we're releasing, or we can just, we can just say unlock Z. I mean, I can explicitly mention it here that we're also unlocking the lock of Z, right? Because we're being restarted. And all right, so now we can just, we can write X. Sorry, we can write Z. Actually, let's make this a bit. So after commit, T1 first or T3 first? I couldn't quite follow that question. Sure. So, in principle, it's up to the scheduler when to exactly restart the transaction, right? But I would imagine that it's the two transactions that are already running T1 and T2, they will just go ahead with the operations, and that T3 is just being restarted whenever there's time for it. Yeah, so we assumed that this was our assumption on the timestamps, right? T1 less than T2, less than T3. Okay, so note that we're using basic two-phase locking. And to make this more interesting, let's assume that we're releasing all the locks as soon as we can. So what is the next operation going to be here in this transaction T2? After I acquire this write lock successfully, I'm going to write Z. Exactly, I'm going to unlock X, right? So I'm going to unlock, I'm going to just abbreviate this as unlock X. And only then I'm going to start writing Z. All right. So the reason for doing the unlocking before the writing is that writing is usually slower than unlocking, right? So I want to release this as soon as possible, so I'm not holding up other transactions. Okay. Oh, couldn't I have actually already couldn't I have done this unlocking step up here, because I'm already done with X? What do you think? No, right? Because I still need to acquire this lock. And as we said before, we only can have a single growing phase during which we acquire locks, and then a single shrinking phase during which we are releasing locks. No, so we know all the steps here, right? So these are all the steps. Let's just assume that this is the full set of operations executed by each of these transactions. So there are no steps omitted here. All right, so the reason why I can't do this unlocking before is because I still need to acquire some locks. All right, so now we've written Z, and then so you could, but in principle you would want to release the locks as soon as possible, right? So I would say that the unlocking should happen as soon as possible, which is at this point here, which is after you acquire the last lock that you need. So you don't want to first do a write, because a write might take a much longer time because it needs to write things. We don't know how large this object Z here is, whereas unlocking is usually just involves like flipping a Boolean somewhere, right? That is usually something much faster. Okay, so now that we've written Z, we can unlock Z, and then we can commit. Okay, and then we get to well, then it really depends on whether T3 gets to, when T3 gets to be restarted, right? And yeah, I mean, in principle, we would just now go to T1. So we need to acquire the write lock for Y, and then we can write Y. Then we acquire the write lock for X. And then we can, what am I going to do next? Exactly, I'm going to unlock again, right? Because I'm not going to write first. I can already start unlocking, so I'm going to unlock Y. Then I'm going to write X. Then I'm going to unlock X. And then I'm going to commit. Okay, and at some point down here, I will actually restart T3. So I'm just going to have all the operations for T3, which are now very simple because no one else is interfering with T3. Okay, any questions about this? So what would have happened if we had used the wait die rule? So we wouldn't have restarted T3, right? Okay, so before I tell you what would happen with the wait die rule, so there's one question in the chat: why we can get long after? Sorry, I don't understand the question. Why can we get the lock in T1 after the other transaction released the lock? So, you know, at this point here, the transaction here don't hold any locks, right? Transaction T2 unlocked all the items that it locked. So we can easily acquire locks here. Was that your question?
Maybe maybe the answer is touching what ask you why doesn't the T2 may want the T1 T2 doesn't want T1.
T2? I mean, T2 is already finished here, right?
Yes, so T2 is already commit and finished. So
yeah.
So it's recoverable and no conflict between.
No. So it doesn't say that we. Okay, I think there's some general confusion here. So, you know, this growing and shrinking phase here is only for each transaction, right? It's not like globally. Okay, so this is, you know, like each transaction can only have like a growing phase and then a shrinking phase, a growing phase and then a shrinking phase. But that doesn't mean like there's like, if you look at these operations in a like in one global fashion, that there's a single global growing phase where only acquire locks and then a single global shrinking phase. That's not necessarily true. So, okay, there's a question: what if T2 commits after T1? You mean if I just move down this commit here all the way? Yeah, I mean, that wouldn't change anything as long as I don't change the order of these operations here, right? Because I still have already released everything up here. It doesn't matter whether this transaction has committed or not. The point is that I've already released the locks. But if I know that it has committed, then it must have, you know, at least for basic two-phase locking, it will have already released the lock. For strict two-phase locking, it releases the locks only after committing. Okay. All right, so coming back to what would happen here when I use the wait die rule instead. All right, so transaction T2 has a smaller timestamp than T3, and we're using wait die. So what will happen? Well, it will just wait, right? It will wait, and it won't restart T3. Okay, there's another question. Why is the unlock after the other lock unlocked before C? So only for this one here, only for strict two-phase locking, you must unlock after committing, right? C means commit. But for strict two-phase locking, if we assume strict two-phase locking, which we're not here, we're assuming just the basic two-phase locking. So in strict two-phase locking, you can only unlock after you commit. Okay, so in that case, these operations would need to happen afterwards, after the commit. And also this one here. All right. But that's true, as I said, only for strict two-phase locking. It's not necessarily true for basic two-phase locking or for conservative two-phase locking. All right, so yeah, we still have 10 minutes left. Okay, so any other questions? Any other questions? Then I just finished this example here with the weight die rule instead of the wound weight rule. All right, let's do that. To erase some things though. So I got some direct messages. So what if the locks acquired by transaction in C2PL is a conflict with each other? Well, that's not possible, right? Because in conservative two-phase locking, you only acquire locks in a transaction, and in particular, all the locks that the transaction needs, if you can acquire all the locks that the transaction needs at that point. So if you have two transactions that would conflict, one of them needs to be the one that comes first, right? So if you have T1 and T2, and there's some conflict in terms of the locks that they need, so one of the two transactions needs to be the first one that acquires all its locks. And at that point, the other one can't acquire any locks anymore. So it's not a problem. Okay, so, all right, so let's look at the weight die. Okay, so in this case here, when we try to acquire this right lock for writing Z, now since T2 is younger than, older than T3, it will wait, right? So it's just blocked. Okay, and so it also can't commit, obviously. So next in turn is T1. So T1 will try to acquire a lock on Y. And it will succeed because nobody has acquired a lock on Y. Then it can write Y, and then it will acquire a lock on X. And, or rather it tries to acquire a lock on X. Okay, so what is going to happen now? Exactly, it's going to be blocked, right? Because T1 is the older transaction and it's waiting for a younger transaction here who already holds a lock, okay? So T1 is blocked, T2 is blocked, and now T3 gets to continue. Note that T3 is not blocked. So T3 now wants to acquire a right lock on Y. Okay. So T3 wants to acquire this right lock, but unfortunately, T1 currently holds a right lock on Y. So we have a problem, right? Because now T3 is the younger transaction. It has a newer timestamp. Okay. So in that case, it will do what? What is going to happen here? Exactly, it will lead to a restart. So all these operations here are rolled back, and the lock on Z is released. Okay. So in particular, this will allow transaction T2 to progress. So it can finally proceed to write Z, but again, before it does that, it will just unlock X, just like before, for the same reason, and then it will finally perform the write on Z. Okay, and yeah, also this transaction, you know, it can now acquire the write lock on X here, because now we unlocked X. Okay, so this can now write X, but actually it will first unlock Y. Then write X, and then we can unlock Z, and commit and unlock X, and also commit. And at some point down here again, T3 will restart. All right, good. Okay, so yeah, this brings us to the end of, okay, there's another question. So unlock Z in T2 is before unlock Y in T1. Yeah. Yeah, strictly speaking, yes. Yes, it's open book. So I actually don't have a past final paper because, as I said, this course has been always taught by multiple people. I mean, multiple sections by multiple people. And I think there's this policy of not uploading any old exam papers. But the practice quiz, I mean, the practice questions that I will upload, so they are taken from previous exams. So you'll get some there. So the solutions to homework 2 should already be online, unless somehow they're not available. For the ones for homework 3, we're going to wait until after the deadline for obvious reasons. All right, so I guess this brings us to the end of today's lecture, and in fact, to the end of this class. And yeah, we're going to see each other during the final exam, I believe, at least online. So best of luck for that. There's one question: if the log records. So the exam will only include things that I've taught here in this class or in the tutorials, right? So anything that was taught in the tutorials, homeworks, or in class is included. That's the usual assumption that you can make. All right, yeah, it was a pleasure teaching you. And yeah, maybe we'll see each other in real life at some point. By the way, unfortunately today there aren't any office hours, but I will hold one more office hours on Tuesday instead. Okay. Well, that's good to know. It was a pleasure teaching you. Okay, I will close the lecture now. Thanks everyone for joining.